Hi, everyone. Welcome to Advancing the Revolution in Photopolymer 3D Printing Performance. My name is Tess Smith, and I will be your moderator today. Just a few housekeeping notes before we get started. At the bottom of your screen, you'll see a section for Q&A. Please use this section to ask any questions. We'll be answering your questions at the end of the presentation, and we will do our best to answer as many as we can. Any questions we aren't able to get to will be sent to an expert who will reach out to you directly. Please note this webinar is being recorded and will be available soon. At this time, I'd like to introduce you to today's speakers, Marty Johnson and Matt Westman. Marty Johnson is a technical fellow at 3D Systems and is part of the core team that develops 3D Systems Figure 4 platform. With a background in mechanical engineering, Marty has extensive experience working with injection molding tools in different plastics and brings this perspective to his work with additive manufacturing to deliver solutions that balance speed, accuracy, cost, and performance. Matt Westman is a senior materials characterization scientist at 3D Systems with over a decade of experience in polymer development and is an expert in mechanical, thermal, and thermomechanical characterizations. Matt is a leader in developing weather and long-term stability characterizations at 3D Systems. As an active member of multiple standard organizations, including ASTM and CMH17, Matt is committed to bringing the next generation of production-ready polymers to additive manufacturing. At this time, I'd like to hand it over to Marty to get us started.
Thank you, Tess. And really glad to be here and really glad to be talking about photopolymers and additive manufacturing. A lot's happened and a lot's changed in the history of photopolymers and 3D printing. And we're looking forward to presenting some of that and what some of those challenges have been and how we've really moved that forward. And a big part of that's going to be through looking at how we've achieved long-lasting mechanical performance and stability, and then why that's important, why long-term environmental stability is critical to advancing advanced additive manufacturing technology. So Matt's going to take you through and look at the historical challenge of photopolymer 3D printing. And before we get there, I just want to take a quick look at what are some of these advantages and challenges. One of the things that have been really good about additive manufacturing is the aesthetic part quality. Photopolymer 3D printing is known to deliver the smoothest surface quality. You can get really nice fine detail, realistic plastic parts, and get parts that are really close to what you see in injection molded quality parts. So you get the smooth sidewalls and you get the feel of the plastic. And so that's one of the really nice things that's happened with the materials and the technology in additive manufacturing. And then you follow that up with the overall versatility. And there is a lot of versatility in additive manufacturing for looking at materials, looking at designs early in the product development phases, looking at different ways of prototyping parts, the ease of printing, what kind of geometries you can do in additive manufacturing that cannot be injection molded, and how do you put some of these parts together in ways that you can innovate and move and to get some of the different products and solutions for different applications. But when you get to material performance and longevity, that's been the problem for additive manufacturing for photopolymers for quite some time. And so over 25 years of use, these materials have advanced, they've gotten much better, but getting to that long-term UV and humidity stability, that's been the real challenge. And part of that is, what are the mechanical performances that you get over time? Do your parts become brittle? Do they change color? How can I use my part 2 years from now the way that I can use it today? And so these are some of the things we'd like to address today as we go through and look at the different photopolymers. So Matt, why don't you take us through achieving and how we got to long-lasting mechanical performance and stability?
Thank you, Marty. So as 3D Systems went to approach the challenge of addressing long-term stability, the first step in this process was developing a case study and developing a material that was well characterized. Many years ago, when we went down this path, we selected one of our early figure 4 materials and went and began characterizing it and developing large data sets using a weathering chamber known as a QUV. This uses a fluorescent type UV light source to replicate validate ASTM outdoor and indoor testing. Specifically, we were targeting the ASTM standard, ASTM G154, which is the outdoor weathering standard for polymers. And in this case, we were just looking to explore and understand what our material base was. After we thoroughly characterized our material, one of our materials, and developed a case study, we were then able to generate these really lovely curves that projected hours of exposure and plotted as a function of decay of mechanical properties, which is really great. But without having any baseline or relevance to show, it's very hard for customers to understand what 200 hours in a QUV replicates. And so the next step in this process, and this path that 3D Systems took, was actually doing actual weathering of samples. We went and selected 3 of our North American sites that had very unique weather environments or environmental factors. We included weather environments, sites such as our Rock Hill manufacturing, our headquarters, which is going to have a more of a hot and humid type of environment. We also looked at other sites as well within our portfolio that had other environments that were more moist and humid, like in the Pacific Northwest, or very dry and arid conditions like you would see in the Mediterranean or in Central California. And in those cases, over the course of several years, we characterized and measured many different materials and plotted them relative to what we were seeing in our QUV. It was through that course of several years that we were able to generate an acceleration factor internally that allows us to transform our hours in the QUV into weeks, months, or years in actual outdoor data, which is really key and beneficial for the customers, because at the end of the day, hours in QUV, like I said, hours in QUV are really not relative versus having that understanding that 200 hours in the QUV equates to 5 months outdoor actual exposure. And over the course of those years, what we found is that most of our materials perform very uniformly in all 3 environments. And that allowed us to have the stability and the understanding of our materials to move forward and continue to do that work to this day, such that every year 3D Systems continues to validate both stabilized and unstabilized formulations that we are developing as we continue to push the barrier of additive manufacturing further and further, and as we develop new chemistries. Next slide, Marty. So like I said, after we've developed these acceleration factors, we then went and developed some very novel chemistries and chemistry packages that were providing us best in class and really unparalleled weathering stability that you don't see in the additive space. As Marty alluded to earlier, typically additive parts and UV photopolymers specifically are very well known for becoming brittle over time. This is only exacerbated when you put them outside with a combination of both the sunlight and the moisture. This combination really drives the degradation of the polymers. And so you see a traditional degradation curve like we see here on the left with a traditional UV cured photopolymer. And in this case, we see that the material at just a few years equivalent indoor weathering, in this case, really drops off and the material becomes quite brittle, and we lose 75% or more of its elongation within a very short window of time. The unique and novel chemistries that 3D Systems has patented has really allowed us to expand and open up that space for outdoor and indoor weathering and created very nice long-term stability as shown here in the green curve. The same is similar chemistry with our Pro Black 10 material, when properly stabilized, shows incredible performance over an 8-year period of indoor weathering. Likewise, when we look at a material like an elastomer, rubber 65A for instance, we see really best in class stability in outdoor and indoor stability. Traditionally, for photopolymers, and specifically elastomeric photopolymers, they have a very, very poor performance outdoor. We typically see them degrading much faster than the blue traditionally UV cured material we're showing here is. But with our novel chemistries and technologies, we're really extending the lifetime of these materials well out past 1 year stability and out into the 18-month or multiple years. aside from mechanical stability and tracking change in properties over time, another aspect of long-term stability that 3D Systems is looking at is in color stability. Once again, with our traditional photopolymers, we know that the materials, as they degrade, they also have a tendency to turn brown, turn black, discolor, and turn yellow. This is a well-known defect or well-known issue with photopolymers. With the new Figure 4 photopolymers, specifically the UV stabilized production ready materials, we see that we can take similar materials, in this case, Figure 4's rigid gray, and after 18 months of accelerated weathering, we can show that we have no visible change in coloring. This is a real game changer when we're talking about stability for materials, because previously all of any gray material you would see would end up looking brown like we see up here in a few months to within a year's outdoor. This is really going to give we really believe this gives customers the opportunity to design and develop materials for long-term applications, and they'll have that confidence that the material will not only perform well, but it will also look really, really well. Another example is our new Figure 4 rigid white material. This is another long-lasting material with excellent weathering and stability performance, but it also maintains its clean, opaque white color over long periods of time. In this case, we are showing 2 years color stability, which is just fantastic. Traditionally, photopolymers within months to even a year would have yellowed. And our new Figure 4 materials are showing excellent stability out to 2 years outdoor, and in some cases 10 years indoor weathering.
Thank you, Matt. And so one of the things when you look at this kind of data and you look to see where these materials are lasting longer, not just for elongation, but for tensile modulus, tensile strength, your notch impact, all of your mechanical properties are pushing out. And now we're looking at these in years and not months. What do we do with that? And, why are the UV and humidity stable charts and data and materials and changes so important? So, and let's look at that, because the reason why is that you now have long-lasting parts, additive manufacturing with long-lasting parts. And what that leads to is you now have different, more vast applications that you can address as you look at this with the different materials and see where that goes. So a few of the places we want to look at today are production goods and where the benefits of long-lasting parts come in, contract manufacturing, where people are engineering to product manufacturers, OEM products, things like that, that contract manufacturings now have more tools to be able to advance some of the things that they're doing. Manufacturing aids, guides, rails, diverters, jigs and fixtures, what kind of things that need long-lasting applications so that they can be used to advance the manufacturing lines and even make those safer. And then you get into clinical trials, and this is where the color stability will come into play, and we'll look at that a little bit as well, because the color stability, especially for white materials, is really critical for things that you need to push out over time. So we'll start with the production consumer goods. And if you look at the table to the left, you're looking at some different consumer segments, some different things, electronics, consumer appliances, sports and fitness, even out to outdoor goods. What are the kind of warranties that you see on these? So some of the things that you see listed here in this table are some of the average warranties you'll see for these types of products. Well, if I've got a product, for instance, if I'm doing a gaming console for consumer electronics that has a 2-year warranty, and I have additive manufacturing parts for that, well, then I need to be sure that I can cover the shelf life for that material, for those parts, which a lot of times is a year or 2 years. And I also want to be able to cover the warranty for that part. So the long-term stability enables me to now start looking at, I can make parts through additive manufacturing for end-use production. And it's enabled by the ability to have the long-term stability. So if you look at that, you start looking at extended warranties. A supplier is not going to go through and just extend an extended warranty. They can go through and look at the data. They can look at the risk analysis. They can look at the life of the part. And if they have a life of the part and they know that part's going to be the same color, they know that part's going to have the same mechanical properties after something comes out of the package and through the life of that product. Now they can with confidence go through and put out these extended warranties. So the in-use production consumer good capability that's come through this long-term stability is very good option for the different applications that you see. This also translates over to automotive, aerospace, and other industrial industries where you may even have higher requirements for part stability. And so let's take a look at contract manufacturing. And you can kind of look to the left. There's a aftermarket camera that goes onto the back of a vehicle. And the aftermarket camera is bare. So contract manufacturer went in, took a look and said, we got a solution to that, because when these cameras get rain on them, you can't see, you can't back up, aggravating in the morning, backing up out of the driveway. Well, now to keep that rain and keep the dew off of the lens of that camera, they went in and developed a cover. This is something they could go in, they could use that cover because they know the cover is going to last. It's going to have the same properties out to 5-8 years. And it gives them the ability to start creating and innovating on some of these OEM type products and aftermarket type products. So these contract manufacturers now have, as I mentioned, a really good tool that they can go in to start producing these type of products. This is a real good example. This is a Flex Black 20 here. You can see the chart. You know, this is a material that's really tough that you need for an application like this. And you can see this, the elongation at break outdoors is only gone down to about 11% loss in elongation at break out to 8 years. So this part's going to maintain and work for a good long time. Another great place that long-term stability translates is the manufacturing aids. And manufacturing aids need long-lasting parts. And one of the nice things about manufacturing aids, when you see an assembly line, you see a lot of rails, you see a lot of diverters, and the system's built and comes up. But during that manufacturing life, this manufacturing line, you have wear, you have new innovation, you come up with new ways to make this manufacturing line more efficient. You find guards and things that you can put in that make the manufacturing line more safe. And so you can really start to create products that can go onto the manufacturing line to enable that to be more efficient. And the reason you can do that is these parts are not going to become brittle. If you had a part that's going to become brittle in 2-3 months, that's not something that can really take that wear and tear that can go into something that would be disruptive to your manufacturing and drop your efficiencies and drop your yields and drop your safety, as you can use this for guards and things like that. So it's a really nice thing to have when you can go in and print and customize and do these types of things to your manufacturing line. You also get into jigs and fixtures. You can see the picture on the bottom left where you've got a cutting tool and you go in and you set that cutting tool and it sets the depths, and you can, the part that you see in the center was used to set a depth to cut the part on the left to the exact position that you see on the right. Lots of different manufacturing and custom jigs and fixtures like this are available because of additive manufacturing and the plastics that you can use through this long-term stability, because now this cutting tool is something that can be used out past months and into years as long as this product has life. And then you go to clinical trials, and clinical trials can last 6 months, some out past a year. And one of the things you see in clinical trials is a lot of times these products need to be white, and they need to be white all the way through that clinical trial. And what's nice about these new formulations that 3D Systems has, they've been engineered not only for long-term stability for mechanical properties, but for color. And long-term color stability is really critical when you get to something like clinical trials, because now that color is maintained, and the color maintains and gives the good appearance and gives the good result, and it helps get the right data through the clinical trials that you see for some of these products. One thing I would point out, when you have clinical trials, it's more than just color. And so your rigid white, some of the figure 4 white materials all have the ISO 10993-5 and -10 biocompatibilities and are autoclavable. So now when you look at the autoclavability, these materials have now not only been enabled to handle the long-term color stability through environment and through the UV and humidity, You also get the autoclavable color stability that comes with these different white materials as well. And that enables, again, so that you can do some of these clinical trials and things that push out 6 months to a year. And finally, let's take a look at functional prototyping. And functional prototyping is a critical part in the product development cycle. In this particular phase, you're looking for data that can be used to push your product and push your fast learning cycles so that you can get the product to life, to production quicker. You want to see that some of the properties you have, you can use to look at your efficiencies, you can use to look at your capabilities and things, but only if those materials exhibit your end product, or if your additive manufacturing product is going to be your end product in production. And so what's nice about the functional prototyping is a lot of times that functional prototyping lasts out more than weeks. And so you want to have these materials that have the same kind of data at week 6 that you have at week 24. So you really want to be able to push these things out so you can get the right cycles to failure. And if you're failing and you're doing functional prototyping, you want the failure not to be because your additive material failed because it didn't have the right properties, because it lost that due to age. You want it to fail because of the design or because of some other event that happened, so that you have the right data to make the right decision for that product. So long-term environmental stability plays a critical role in this type of functional prototyping, as the integrity of that data remains valid throughout the mechanical properties over a very long periods of time. And so to look at, we've talked about these figure 4 materials, and what's really great at 3D Systems and exciting is to see this innovation with these new materials with this long-term type stability. And so if you take a look at this chart, which has a lot of things going on here, but if you look down the left, you see the tough materials, the rigid materials, durable materials, high temp specialty rubber, and your indirect production. And so you start looking at some of the places we've talked about where I have production and consumer industrial type of applications. And so as you get into production, these line up quite well because all of these have the long-term stability. And when we say all of these, I'm talking about the tough whites, your grays, your black materials, your high temp materials, and the rubber materials, as Matt mentioned, all have been engineered with long-term environmental stability. And so that translates again over into your contract manufacturing, where contract manufacturers can take a look at how to use these different materials for some of the products and some of the OEM type of products that they'll create. And then of course is manufacturing aids, and you go in and you see there's still a vast amount of materials. And what I want to point out is there's a nice portfolio of materials that go through that cover the tough, rigid, durable, high temp, and rubber types of materials. And then you get into medical and clinical trials, and a lot of times those are going to be specific to white materials. Not always, but some of the ones that we just want to point out from the white materials that have the biocompatibility as well as the long-term color stability that we discussed earlier. And then of course your functional prototyping, and a lot of your parts that you use early on in your figure 4, you can use those as well when you get into your functional prototyping to start getting data for your in-use products. So 3 things to take away as we go through and look at these high performance materials, and we look at the new innovations and some of the engineering and why we focus so much on long-term stability with these figure 4 materials is you get high performance materials for the most demanding applications. There's a lot of different applications that can be addressed in the table that we just looked at in the previous slide. Production grade, long-term stability, 8 years indoor, 1.5 years outdoor, and that's what these materials are tested to. Some of these, if you have an application that needs 10 years and you see that a material is still up at 100% at 8 years, then a customer can invest time to go in and test that out further and push it out to 10, 12, 14, 15 years and find out where that point is that you start to see the degradation that would influence the decisions made on an application or in-use part. And of course, the off-shelf injection mold like part quality and the part quality coming from these parts combined with the long-term stability really make these a higher grade, professional grade materials that can be used for many things. So as we wrap that up, I just want to really point out the things to take away and really point out how to use the things that you see in these data sheets. And the charts that you see are listed in the data sheets for each one of these materials. If you go to the website, you can pull those down and take a look at those materials, and you'll be able to push through and see where these match your application and where you may or may not use the particular material for the particular application. And I think we're going to take some time and answer a few questions on this as well. So thank you very much.
Thank you, Marty. As Marty mentioned, we are going to open it up for Q&A. So if you do have any questions, please drop your questions in the Q&A section of your screen. We've had a couple questions come in, or a few questions come in, Marty, so we'll go ahead and get started, Marty and Matt. First question, are all of the materials shown formulated for long-term stability?
Yes. When you go in and see the materials in that chart, they are, with the exception of the bottom row that has the eggshell molding and some of the casting materials, those are made as indirect production. So when you looked at indirect production type parts, those don't have the requirement for the long stability. But when you go into your durables and your rigid, your rubber materials that we looked at, those are formulated for long-term stability. And that's where, if you go in, as I mentioned, pull the data sheets offline. There, you can get them from our website. And when you click on the material, you should be able to go down and pull the data sheets, and they'll have that information, as well as isotropic information, chemical compatibilities, ISO testing. A lot of the different information would be on those data sheets, as well as the long-term stability.
Next question, rubber materials generally do not do well outside. Can you speak to the material being on the outdoor chart?
Yeah, Matt, would you like to take that?
Yeah, certainly. Yeah, so like I was saying earlier, you know, we typically see with additive parts that that elastomers become extremely brittle very, very quickly. As we've shown with the figure 4 rubber 65A, we can retain tensile properties, not just elongation, but we also maintain that tensile modulus, which is really, really critical for elastomers, because a lot of the functionality is tied to the stiffness of the modulus of the material. We don't include, it's not included on our data sheets, but we do generally measure other properties as well. In the case of rubber 65A, another very common measurement that you would see would be a Shore measurement. And in that case, that's another example of the long-term stability that the chemistry is providing in this case, where the Shore value does not change, and it still maintains a 65A Shore plus or minus a couple Shore A units. Yeah, great question.
Great. Next question, how accurate are current cost models for photopolymer 3D printers? Could these models be improved?
And when I hear cost models, I'm assuming this is for all the way for your TCO, or when you get parts out the end. And when I say that, cost models, what you would want to include is, as you get your part and you have the cost model for your part, in part, through post-processing, and the entire time spent should roll into that. And those calculators can be developed that make that pretty accurate. One of the things that I would roll back to that is, from a cost model perspective, by having the life of these parts, one of the nice things that people can do is go in and take the cost model and look at that part relative to their in-use parts. So, and I guess when I talk, what I'm speaking of is, if I have a production part, how does that roll in? If this is a piece of an assembly, let's say I've got a piece of exercise equipment, for instance, and I'm making handles out of the rubber, and I know the rubber black tin makes good handles. I want to put those onto my exercise equipment as an in-use part. Well, one of the things I can look at from the warranties and things from the piece of exercise equipment is that if those handles were worn out, I wouldn't have to replace the handle. I can simply reprint parts, and I don't have to keep inventory. I don't have to maintain a tool. I could even redesign the parts to have a different texture over time. There's things that you can do. So part of that is helps you maintain your bigger pieces of equipment by looking at the parts that go onto that equipment, and you roll that into your cost model and COGS of your in-use part. I hope that worked.
Thank you. Next question, how does the part cost compare to that for parts made from the traditional photopolymer materials?
There's going to be trade-offs. So generally, when you start looking at additive materials versus injection mold materials, the cost of tooling is going to be a big part of that. And so you got the amortization of the tooling. From a lot of the parts, and of course, when you start looking into this, the size of the part is going to make a big difference. But if I've got the part, let's say that it's the size of the size of my mouse for my computer. Well, if I look at that, then I'm going to be looking somewhere around 30,000 parts to look at where that break-even point is for the injection mold. So, and one of the things you're looking at too, and I've talked about this in some other webinars, is when you look at the cost that comes out, what you get from doing the additive is, as you go through that product life cycle, that we looked at the feasibility, the functional prototyping, the production, there's some advantages you get there where you can start, if you're looking at functional prototyping for your part, and the plastic that you're using in your functional prototyping is going to be your end-use part, then your time to market is going to be much faster. The ability to use that tool that you're using to print in manufacturing can be used to make another part later. So it's not a one-time use like an injection mold tool. So those are costs that are not really considered when you look at the actual part cost. And then not having to maintain, as I mentioned, tooling or inventory for parts down the road. You only have a CAD file that you go in and you reprint your part. But the fact that in production, you can go in and have the flexibility to print multiple parts. So if I use the mouse as my example again, I may want that mouse in 3 or 4 different textures. And so I've got 4 SKUs of the same type of geometry. I don't have to have 4 injection mold tools. All I've got is that printer, and I can go change my CAD file and the texture on that file and use that printer.
Thank you, Marty. Next question, do you have a material that is equivalent to polypropylene and its chemical resistance? Matt, can you take that question?
Yeah, certainly do. In the figure 4, polypropylene is well renowned for its chemical compatibility. And within the figure 4, we have some materials that perform fairly well, but unfortunately we don't have anything that's going to perform across the board as well as polypropylene within the figure 4 space. Now that being said, we do have other materials in our other technologies. Specifically, we have a polypropylene material on our SLS printers. So if you are looking for polypropylene-like compatibility, we are now actually offering polypropylene as is on our SLS platform.
Great, thank you. Next question, which materials are recommended for use in medical grade products?
I think that's where you're going to want to jump in on the white materials. When you start looking at the white materials, and one of the places you're going to see is the white materials have been tested and are biocompatible per ISO 10993-5 and -10. So when you start looking at medical materials, you want to start and be sure they have it at a minimum, those 2 different classifications. And so you'll see that in the figure 4 rigid white, the figure 4 Med White 10, the figure 4 Tough 60C white. And then you also have that same capability in the Pro Black 10. You've got that in the Rubber Black 10 and in the Rubber 65A. And one of the reasons the rubber materials get that is because if you want to use those for grips and things on something like exercise equipment, then you actually need to have that type of biocompatibility on those as well.
Next question, are there any materials that work only for prototyping or only for production uses?
One of the nice things about these materials is once you get into production materials, any production material is backward compatible to prototyping. But let's take a quick look at the table, because when you go through and look at the particular materials, one of the things that typically tends to lead itself to more prototyping is going to be some of your faster printing materials. So a lot of times you'll see the rigid materials, for instance, will be used for prototyping because they're faster printing, where you're at 50, 60 millimeters per hour versus 25. So if you're trying to get parts out the same day, but it really depends on the fast learning cycle that you're after. If it's next day, any of these materials, you're going to have parts the next day that you can use, and you can print a stack of parts that you can use so that you have those for doing a lot of different prototyping testing. So typically, if you look at the column to the right where it says functional prototyping, you practically see every material. And it is because of that as you move those production-like properties, the long-term stability is actually helping you with that. And so you're getting the ability to do each one of these columns with the same material.
Great. Next question. We talked about white material stability. Can you touch on any other colors?
I can, because when you get into long-term color stability, and that's a great question, because we all have seen the black materials on automobiles and other different types of motorcycles, outdoor equipment. You'll see the black materials start to fade over time. In fact, the gray materials you can see start to fade. That is, again, one of the things we look at in this long-term stability testing, and we probably don't talk about the black enough because it never changes. We don't see the black material fading in this type of testing when we go through and look at this accelerated testing. The rigid grays have a tendency to turn green and brown over time, and these particular materials do not. They hold their color stability, as you saw on the previous slide, where we were out at 8 years, and the part looks exactly like it did when it started the accelerated testing. So great question.
Next question. How do factors other than elongation at break affect the longevity?
So when we looked at this, a lot of times we'll look at the elongation at break because it's really giving you an idea of how brittle a material becomes. However, elongation at break, and a lot of times in an application, it's not relevant. If I want to look at, let's take the Tough 60C white, and I've got white vinyl siding, and I want to put some kind of guard over my lights, and I'm producing guards or diverters for my floodlights or outdoor cameras and things like that. Well, when I print that material, I don't want this white material to turn yellow. I want it to match what I have on my house. And one of the nice things about these type materials, because of the color stability, because the tensile modulus is really good, I can just take and put holes and screw these parts in. And so elongation is never a part of that application. It's a static part. There's no load on those parts. And what I'm really relying on is the HDT of the part and the color stability of the part, that those are not going to change over time. And so I can look at the different properties and use that. Another way to use this is to go look at your tensile modulus. And when you see the tensile modulus, what will happen there is as parts become stiff, and this happens when you get into your rubber materials, is when your parts become stiff, you'll see the tensile modulus start to go up. So that's another way to go look at the data sheets, and you pull the charts and you start to see where does the data start to rise and have a trend going up. Then I know at that point is when, through those years that we're testing, that my part is starting to become stiff. So elongation at break looks at the brittle materials, but that may not have to do with the application, as I mentioned. So you can look at the tensile modulus, you can look at the impact, and you have to be careful with the tensile strength. The tensile strength is a good indicator, where if you have a low elongation at break to start with, your tensile strength, because of the nature of that ASTM test, is going to tend to track what your elongation at break does. So if you've got one of the high temp or specialty materials, such as high temp 300, it has a 300 CHTT, but it's only got a 3% elongation. So because it's got that lower elongation, obviously tracking elongation over time, over 8 years, a 1% drop's going to be, or 1.5% drop's going to give you a 50% reduction in elongation, where really you started as a brittle material and you went to a brittle material. But when you look at the tensile strength, you got to be careful not to overread that chart, because the shape of that chart is going to be similar to your elongation. So that's where you jump over to your tensile modulus and be sure that your tensile modulus is flat as that moves out based on what that application may be.
Does improving UV stability affect photopolymer curing time?
It does not. The UV stability is part of the formulation. So the formulation has many components that drive what that material is going to do. So, and that's why we say it's engineered in the formulation. There's a real reason that we have not seen long-term stability in additive manufacturing for a long time. And it's one of the nice things at 3D Systems because we have senior material scientists that can go in and chemists that can go in and innovate on these different formulations. And in all honesty, Figure 4 is a real breakthrough for additive manufacturing, and what sets it apart from a lot of different products is this long-term stability of these materials. And so as you go in and start looking at the post-cure time, it's going to vary depending on what the full material chemistry is, including viscosity and things like that.
Great. You touched on material that has 60% elongation. Can you talk more about that material?
Yes, when we were looking at some of the contract manufacturing parts, there's a chart on there that has Flex Black 20, and it's a very good catch. This material starts at 60, 70% elongation at break, and after 8 years, it's still there. One of the things about this particular material, this is a durable material. It's got a tensile modulus down around 800 to 1,000 megapascals, flexural modulus in that range. And then your notch impact is up about 91 joules per meter. So you've got a really tough, durable material because it's got that give to it because of the low tensile modulus, but it's got that really high elongation and it's got a really tough impact resistance with that 91 joule per meter impacts. That's an incredible material, and it actually prints very, very well. So yeah, it's a good catch picking up that material because that's a material that you can do a lot of really tough applications with.
All right, next question. We actually have a question for the JCast Green 10. Are these materials not appropriate for burnout in an investment application? Our goal is to create a positive printed pattern and then investment cast it for a lost wax type process for jewelry making.
The JCast Green is used in burnout. In fact, it's got a very, very low ash content. The Jewel Master Gray is more used for master patterns and things like that. So it's a little different type of material, and it's not really the type of burnout wax that you get in the gray and the green. But the JCast Green is used for that. We actually have a jewelry offering. If you go onto the website and go through the jewelry, you can get a lot more on that information and on that material, and you'll see some of the applications there as well that might be helpful.
And can you guys talk about print speed versus different materials?
Yeah, one of the things, if you look at the materials chart, I can kind of just give you a ballpark, but your rigid materials are going to be some of your faster printing materials. Those are going to be 50 to 60 millimeters per hour, depending on the material. They'll be up to that range. Your tough materials are going to be around 25 to about 35 millimeters per hour. And then your durable material is going to be down around 25 millimeters per hour. The high temps can vary. The majority of those are going to be in the 40 millimeter per hour range. And then the rubbers fall kind of in that range as well.
Great, and we have time for one more question. Were any other factors measured or just long-term environmental stability?
So from a production perspective, the long-term stability, it measures the mechanical properties. So you'll see, as I mentioned, the tensile strength, tensile modulus, elongation at break, and elongation at yield. We do have mass uptake data on most all of these materials. If that's something that's, if you contact us, we can go in and get that. But the other part is, from a production perspective, one of the things we did is we make sure in the data sheet to have isotropic data, which is very important when you're looking at something and you're looking at organic parts, what's the isotropy of the mechanical properties? And that will play a role into your part and material selection. And in addition to that, there is an automotive fluid compatibility from US CAR 2, and then there's an ASTM D543 spec for chemical compatibility for industrial detergents and cleaners. And so you'll see the same mechanical properties tested in the long-term stability and those other tests so that you can look and comparatively see to help dial in what material you need for an application.
Thank you for joining us today. We hope this information has been of value to you. If you asked a question and it wasn't answered in our live Q&A, an expert will reach out to you shortly. As a reminder, we are recording this presentation and we will be emailing the video out in the next few days. Thank you, Marty and Matt, for sharing your expertise today. I hope you have a good rest of your day.
Thank you. Thanks, everyone.
And thank you all for joining.